Today's lesson is on measuring earthquakes, and specifically we're going to be talking about the Richter scale, this first one. There are three commonly used scales for measuring earthquakes: Richter scale, Meijerkali scale, and then kind of the new one is the moment magnitude scale. And it is actually kind of supplanting the Richter scale as one of the measurements of choice. But we're going to start with the Richter scale and go over it in depth, and then we can talk a little bit later about the moment magnitude scale and see why it's maybe becoming a little bit more popular. So the Richter scale is a scale that measures an earthquake's magnitude. Well, what's magnitude? Magnitude is a measure of the ground movement and energy released at the epicenter. So a measure of ground movement / energy released at the epicenter. Basically, ground movement, energy released, they're all tied together. The more energy released, the more ground movement there would be. The Richter scale assigns a number based on the ground movement or energy released, and we're going to be seeing those numbers coming up. They calculate, or they find it, by comparing the amplitude with the time lag on the seismograms. So remember, we spent kind of the last couple lessons finding time lags and finding amplitudes. Now we can see kind of how important it is, and you'll be doing that with a nomogram on your labs. You'll compare time lag and amplitude, use a nomogram, and you'll be able to calculate the magnitude. So you'll do that in lab. The Richter scale was created in 1935 by an American seismologist, Charles Richter. It is a logarithmic scale. You might not have learned about logarithmic scales in math yet. I'll do a quick example of what logarithmic means on the next slide. Basically, the ground movement and energy released increases exponentially for each Richter scale magnitude number. So it's not going to be the standard linear scale that you're probably used to. It's going to be an exponential scale. Like I said, if you don't understand that now, we're going to demonstrate on the next two slides. So this idea of logarithmic or exponential. So the amount of ground movement increases 10 times for each magnitude increase. So ground movement increases 10 times for each magnitude increase. The energy released increases 32 times for each one magnitude increase. So for example, a magnitude 2 is not twice as much or twice as powerful as a magnitude 1. A magnitude 2 is 32 times the energy of a magnitude 1. A magnitude 3 is not 3 times as much. It's 1,024 times as much as a magnitude 1. A magnitude 4 is not 4 times as much. It's 32,768 times the magnitude 1. Magnitude 5 is not 5 times as much. It's 1,000,000 times stronger. So it increases very quickly. Okay, if you and when you get to high numbers like a magnitude 9, it's this huge number. So we have what? Thousands, millions, billions, a trillion. So magnitude 9 is not 9 times bigger than a 1. It's over 1 trillion times bigger than a 1. So the power really increases dramatically. You'll see maybe when you're researching for your project where the different articles are arguing or different scientists are arguing about whether it was like an 8.0 or an 8.1 magnitude earthquake. And you think, well, who cares? It's a 0.1. In these upper realms of the magnitudes, a 0.1 is huge. A 0.1 might be millions of times stronger than the other one. Okay, so it's just a tenth of a magnitude might be way, way, way stronger, millions of times stronger, because of how this scale goes. And I'll show you on the next slide a graphical representation. So if you don't quite understand this, here's a graphical representation of what the Richter scale is. So you see in the line here, this is showing you your magnitude, and then it's showing your energy released. And as it goes up, it's getting steeper and steeper and steeper and steeper. This is different. If you had a standard linear graph, it might look something like this, let's say, where a 1 was a 1. So example, a 1 was a 1, a 2, go up, it was a 2, a 3 was a 3. That would be kind of a standard linear scale. The Richter scale is not that. It gets really strong really fast. So when you look at the 7, so if you trace the 7 up here, okay, and then trace it over, 10 to the 7th ground motion, we go up here, look at how much stronger the 8 is. It's this big of distance stronger. The 9, we go up ooh, we don't even make it onto the graph up here. So really, really, really strong. So it increases dramatically because it's increasing exponentially. The bigger it is, the larger it goes up. And even a tenth of a number is really big. If you had an 8 here, an 8.1, might be way up here. So kind of this increase vertically, as you might see, down here, you might see a 3 magnitudes or 4 whole magnitudes. So it really increases dramatically. Well, why do you think Richter did it like this? Do you think most people understand this logarithmic scale? No. And Richter didn't even want his scale to be made public. He wanted his scale just to be for scientists because he understood that kind of normal people, most normal people wouldn't understand this scale. Why did he do it like this, though? He did it like this to keep the numbers manageable. So we could have a magnitude 4 or magnitude 5.2. If you didn't have a scale like this, you would have things like a magnitude 1,099,511,628,000. You would have huge numbers for these big earthquakes. Well, that's not very easy. So he made it this way so you could say, oh, it was a magnitude 9. Much simpler number. And he didn't want it to get out to the public because he knew that the public kind of wouldn't understand how complicated it was. But, so there it is, that's kind of how it works. So a few characteristics about the Richter scale. How many magnitudes does each earthquake have? It only has one. Remember, it's how much the ground moved or how much energy was released at the epicenter. So there is only going to be one magnitude for that. So if we say there's a magnitude 8.9 earthquake, that's what it was. No matter where you measured it around the world, you're going to get it to be an 8.9 earthquake. And I'll show you in the lab how you do that, and you get the same one. You think, okay, if it's farther away, if the recording is farther away, shouldn't it be a smaller number? Well, but then you'll have a bigger time lag, smaller amplitude, it'll all work out. And we'll look at a nomogram, and you'll see how that works. What is the top limit for the Richter scale? Well, technically, there is no upper limit. Realistically, though, we're not going to get to a 10. No rocks are strong enough to hold together under enough pressure to get a magnitude 10. We've only had 6 earthquakes that we know of in history that were 9.0 or above. You can see Chile 1960, Alaska 1964, Alaska 1957, Lisbon 1755, Sumatra 2004, and then Japan 2011. Then kind of the last ones, we had already mentioned this. At high magnitudes, even 1/10 of a magnitude is a tremendous increase. And it is because of that logarithmic or exponential idea that we talked about. Then kind of the last slide here just again shows you a little bit about the power. And that graph showed a little bit about the power too. We see a magnitude 2 is like a ton of TNT or a ton of dynamite. Magnitude 3 is 32. So again, we're seeing this idea of energy release going up by 32s. So magnitude 4 is 1,000, basically, 32 times 32 essentially. It's about 1,000. So you see it kind of increasing. And I left this up there. We said, like I said, 10 is about, you're never going to really get to a 10. So I just put this up here because I thought it was interesting. A 10, they say, would be like a San Andreas type fault that would circle the whole Earth. And if you could get a 12, it would rip the whole Earth through the middle. Again, we're not going to get 10s or 12s. Okay, no rocks are strong enough to build up enough stress to get to them. If we're getting 9.5 or something like that, that's probably going to be about as high as we're going to get. And that's it for the Richter scale. So next lesson we'll talk about Mercalli scale and then hit on the moment magnitude scale a little bit.